All right, let's dive right in. Today, we're going to tackle a real cornerstone of calculus and physics, second-order linear differential equations. Now, I know that sounds complicated, but these aren't just some abstract math problems. Nope. This is the language we use to describe the world all around us, from something as simple as a bouncing spring to the super complex behavior of an electrical circuit.
So, how do we even begin to talk about things like acceleration and forces using math? Well, the answer lies in something you already know, the second derivative. The first derivative gives us velocity, how fast something is changing. But the second derivative, that y double prime, that gives us acceleration, the rate of change of the change. It lets us level up and actually model the dynamic forces that shape our entire physical world.
And this right here, this is the master blueprint for those models. What this equation does is it relates a function, y of t, to its first and second derivatives. Now here's a really crucial point. See that g of t on the right side? If that thing is 0, we call the equation homogeneous. And that's going to be our main focus today, because that's where we build our foundation.
So here's our game plan. We're going to start with something called the superposition principle. It's this incredibly powerful rule for combining solutions. Then we're going to use something called the Wronskian to do a little quality check on those solutions. From there, we'll build what's called a general solution. And finally, we'll see how to pinpoint one particular solution using initial conditions.
Okay, first up, probably the most important tool in our entire toolkit. The superposition principle isn't just another theorem from a textbook. Think of it as our license to build. It's what tells us how we can take simple little solutions that we already know and combine them into something way more powerful.
The principle itself is actually beautiful in its simplicity. If you've got two ingredients, y1 and y2, and you know for a fact that they're both solutions, you can mix them together in any amount you want. That's what the C1 and C2 are for, and the new combo is also a guaranteed solution. These are basically our fundamental building blocks.
And that leads to a really critical question. It's not enough to just have two building blocks. They have to be fundamentally different from each other. Think about it this way. If your second solution is just like a scaled-up version of your first one, you're not really describing any new behavior. You're just describing a louder version of the old one. So we need a way to check that our solutions are, in mathematical terms, linearly independent.
And that brings us to our quality control inspector, the Wronskian. This is the mathematical test we're going to use to make absolutely sure our building blocks are distinct and robust enough to form a solid foundation for every single possible solution.
Now, I know the formula might look a little intimidating, but it's just a specific calculation. You just multiply diagonally. y1 times the derivative of y2, and then you subtract y2 times the derivative of y1. But here's the key takeaway. The only thing you really need to remember. If the result is anything other than 0, your solutions have passed the test. They're independent, you're good to go.
All right, enough theory. Let's actually see how all this stuff works in a real example. We're going to take two functions, and we're going to verify that they are, in fact, solutions to a specific differential equation. Let's get our hands dirty.
Okay, so this slide lays out the whole process perfectly. For our first solution, y1 equals t squared, we find its derivatives. That's 2t and 2. We plug them back into the original equation, do a little algebra, and boom, it simplifies to 0. Then we do the exact same thing for y2, which is t to the minus 1. And yep, it checks out too. So we know both of these are valid solutions.
And because we have two verified, and we're assuming for now independent solutions, we can apply that awesome superposition principle. We just combine them with our constants, and voila, we have the general solution. This formula describes every single possible function that satisfies this differential equation. Pretty cool, right?
Now let's run that Wronskian quality check we were talking about. So here we have two solutions, e to the 2t and e to the minus 2t. We set up the determinant, then we calculate. It's the top left times the bottom right minus the top right times the bottom left. Be so careful with those signs. That minus in the middle is a really common place for people to make a mistake.
And the result of that whole calculation, it's -4.
Okay, the crucial point here isn't the number -4 itself. The magic is the fact that it's not 0. Since our Wronskian is not 0, our two solutions have officially passed the independence test. They form what we call a fundamental set of solutions, which is just a fancy way of saying they are the perfect building blocks to construct every single possible solution to this equation.
So far, we've built a general blueprint. But what if we need to find the one single solution that fits a very specific scenario?
Well, for that, we need what are called initial conditions. This is how we go from a general plan to a final, unique product.
Let's walk through this process step by step. We start with our general solution. Now, the first initial condition, which tells us the position at time 0, helps us find the value of c1. See how that works? To use the second condition, which is about the initial velocity, we first have to find the derivative of our general solution. Then we can apply that second condition, and that lets us solve for c2. And once we have both constants, we just plug them in to get our final particular solution.
Whew. Okay, we have covered a lot of ground, so let's just pause for a second and quickly recap the most important points from this whole explainer.
So, remember this. Second-order equations are how we talk about acceleration and forces in the real world. The superposition principle is your master rule for building a general solution out of simpler parts. The Wronskian, that's your essential quality check to make sure those parts are truly independent. And finally, initial conditions are what take that general blueprint and turn it into one single, specific answer.
So we've built a really solid foundation for solving these homogeneous equations, where the system is basically at rest. But what happens when there's an external force acting on it? What happens when that g of t on the right side of our equation isn't 0? Well, that is the next big step on this journey.